All right, we're finishing off chapter 19 here with further circle theorems. So there's going to be some new theorems here. I think some of them will be new to many of you watching anyway, as well as some new vocabulary, starting with arcs. So we know that the whole way around a circle is called the circumference. But if we were only going part of the way around a circle, we call that an arc. All right, and if an arc is less than half of the circle, it's called a minor arc. If it's more than half the circle, it's called a major arc. I don't know, I'm colorblind, so I have a lot of difficulty seeing the pictures at right. So just in case you're having the same problem that I am, the minor arc BC is here. The major arc BC is there. Okay, and we have to distinguish whether we are describing a minor arc or a major arc because given any 2 points along the circumference of a circle, we can make both a minor arc and a major arc. Okay, related to this idea is something called a segment. So this is when we take a portion of the area of a circle that's cut off between an arc. So here we've got a minor arc, and that corresponds to the minor segment. Here we've got a major arc corresponding to a major segment. Okay, so here we've got a diagram of 3 points on a circle, and we've got a piece of vocabulary here in bold, subtends. Okay, it's a fancy word. All it means is this. So here's our angle BAC, and we see that the endpoints of that angle at B and C, they meet the circle along this arc. That's all that the word subtends means. Okay? It is true, however, that that arc also subtends a second angle. It subtends the angle BOC. In fact, it subtends a whole lot of angles. Here's another one. Here's another one. Here's another one. Here's another one. Really, any angle that has its endings on the 2 ends of that arc, the arc subtends all of those possible angles. Now, new strange vocabulary aside, hopefully it is clear that any arc subtends infinitely many angles. This is important, but only when we consider 2 particular angle types, at least for now. This angle here, BOC, is called a central angle. It's called a central angle because O, the vertex of the angle, is in the center of a circle. BAC doesn't really have a special name, but it does have a special property, and that is that its vertex, A, lies on the circle. There's a whole lot of other angles that will exhibit this property. This one, this one, this one over here. All 4 of those angles, the 3 I've just drawn, as well as BAC, they all have their vertex on the circle, and the minor arc BC subtends each of them. And all 4 of those angles have something in common. If you look at them, it almost looks like they're all congruent, right? And they actually are, but that's not even the most important thing to know here. No, the most important thing to know is this. It's theorem number 1 for the day. If we have a central angle to a circle, its measurement is always going to be 2 times the measure of an angle on the circle, as long as they are subtended by the same arc. I'm not proving that here. You can see that later in the chapter, but just take a look at this picture here. Would you agree that all 4 of these angles kind of look like they're half as large as the central one, because the central one is going to be 2 times as large as any angle on the circle? Hopefully, yes. What about this angle that I've just drawn in? Now that doesn't look like it's congruent to this one up here. It certainly doesn't look like it's half of that measurement there. Did I just break the rules? No. Because this central angle, BOC, is subtended by the minor arc, whereas the green angle I've just drawn in is subtended by the major arc. And I just want to play around for just a second. So notice that no matter where I put A and B, no matter where I move point P to, the angle here is always going to be half of the central angle. And that doesn't matter really where P is. With chord AP could intersect chord OB. That's all right. This angle is still half of this angle. It could even be such that chord AP goes through the center of the circle. That's all right. They're still subtended by the same arc. It could even be that point P was on the other side of the circle entirely, in which case they're still subtended by the same arc. In this case now that arc, however, is a major one. So this central angle has to be 360 degrees minus what this used to be. But still, the central angle is twice as large as the angle on the circle. Going along with that is theorem number 2, which, I mean, if you believe theorem number 1, you have to believe theorem number 2, right? Because if we have a central angle here, and we're saying that this angle is half of the central angle, but this angle is also half of the central angle, then obviously they have to have the same measurement. So anytime we have two angles subtended by the same arc, and those angles are both on the circle, then those angles must be congruent to each other. So those first two theorems go together. I think they're pretty easy to wrap your head around, not too much to memorize there at all, and I don't know, these are pretty popular, so many of you viewing the video may have already seen these before. Theorem 3 now. This one's a little bit more complicated. A little note here, if you want a proof of this one, you can check out Chapter 19, Section C, exercise number 4. Otherwise, I'm just going to try to explain to you what this theorem says, because I know that this here is a whole lot of words, and that can be tricky to parse through sometimes. So looking at the diagram, what do we got? We've got a tangent to the circle here. We've got an angle here and another angle here, and those two angles are always going to be congruent. So what can we say about those two angles? Well, this is the angle in between the tangent and a chord. That chord, right, is forming a minor arc of the circle here. And the angle which is subtended by that arc is congruent to the angle in between the tangent and the chord itself. I'll try saying that all using different words now. Well, I'm still going to use a few of the same words, like tangent and chord, I guess. So we've got our tangent, okay? And the tangent is making an angle with a chord. It's making an angle with this chord here, AB. Now, AB, that chord, you could think of it as like kind of touching two angles. You've got this angle here, you got that angle there, right, at the two different ends of the chord. Well, the original angle that we were talking about, this one, is congruent to the other angle formed by that triangle ABC, not either of the ones at either endpoint of the chord. Similarly, in the same picture, actually, we could say that we've got an angle here in between a tangent and a chord. That angle needs to be congruent to this one. All right, let's look at some example problems solving for x. In this first one, we've got this central angle up top is 250, but if I look at angle x, that's going to the minor arc AB, whereas this angle is subtended by the major arc AB. But if this top part is 250, what does that make the bottom part? Since the whole way around's got to be 360 degrees, that means that that bottom part's going to be 110. And if that's 110, then I know that x has to be 55, half of 110. Over here, a little more interesting, we've got two parallel lines. That's very exciting. If two lines are parallel, that means that we have alternate interior angles are congruent. So whatever x is going to be the same as what this is, and whatever, well, that's 36, so I know that that's 36 as well. How is this helpful? Well, look, angle BDC, where x is, goes to minor arc BC. But so does this angle, and we just said that that angle has to be 36 degrees. That means that x is also 36. Now we'll look at an example of the other theorem So let's look at this. We've got a tangent connecting to some chords. So whatever this angle here is, it's going to be congruent to that one there. Now again, we have parallel lines, which means that also it's got to be congruent to that one because we have alternate interior angles. So since these two angles are congruent to each other, we've got this isosceles triangle going on. They must both be equal to 130 divided by 2. 65 degrees is our answer. Anyway, that's all for chapter 19. As I said, we're not going to talk about sections C or D, although there's some great mathematics there. And if you really want to push yourself, then I recommend checking them out. We are only responsible for sections A and B. We don't need to know how to prove any of these theorems. We just need to know how to use them in more and more complicated situations. So I hope you learned some things here. I know that I did. Legitimately, the first time I taught this section, I was not aware of the final circle theorem that we saw today. I would have been able to derive it and prove it if I needed to, but just knowing it off the top of my head was not something that I could do at the time. And the word subtends, man, I went like 30 years of my life without ever seeing that word. How lucky are you? You get to learn this word when you're still in high school. Good for you.